So this lecture is devoted to Doobs inequality. Oops, sorry. And I mentioned it briefly previously in the course, and I don't know if you remember, but it's an interesting fact that in probability we study the maximum of um, processes for n smaller or equal than big N, for example. Let's call this Mn. So we study this maximum of random processes, and we study it in several contexts, right? We study this when we are talking about um, random walks. We study this when we are talking about the tightness in Donsker's theorem. So this appears in some forms of law of large numbers. So it's important to see that this variable is studied a lot, especially the probability that this variable is larger than something. Sorry. We studied this probability a lot, and often we relate this probability in a way with the probability that the last point, sorry, of our process behaves in a certain way. So we see that in Kolmogorov's theorem, we see that in Etemad's theorem, and now we're going to see that in Doob's inequality. They all have very different forms, so it's not like all these theorems are just the same. They have very different forms, and one very interesting property of Doob's inequality is that it treats martingales and not sums of IID random variables as the previous theorems I mentioned. So let's state the theorem right away. So suppose that xn is a submartingale, and let us define the maximum mn. So we are taking the maximum for I large, smaller or equal than n of xi, and we're gonna even take a plus here. So we're taking the maximum of the positive part of our submartingale. Let's recall again that the positive part of a submartingale is also submartingale, but this maximum is not clearly a submartingale. It's just this maximum that this process has achieved, but of course it's an increasing thing, so it's also going to behave like a submartingale. And fix some lambda bigger than 0. What this theorem says is that for A being the bad event that you want to measure, where mn is larger than lambda, so this is the event that you want to control, the probability that the maximum is large, its behavior is related to the expectation not of the maximum but of xn. So I'm going to first put the full result and then recall that this is smaller or equal than just xn plus. So here, let's make several comments before we go to the proof of the theorem. First, why this inequality is true. This is going to be the easy part of the proof. So of course we can always remove the indicator function and this expectation is going to increase. Secondly, we can put the positive part here and this expectation is again going to increase. So this is okay. Now, if we look only at the first and last terms, you see that it looks a bit like a Markov type inequality, where the probability that a random variable is larger than lambda is bounded by 1 over lambda times the expectation. But there is a strange thing going on here. One side has the variable m, while the right hand side has the variable x. So yeah, again, it's one of these shapes of theorems where the maximum is being deviating is relating to the probability that the last point deviates. And now we're gonna give a full proof of the theorem. In the next class, we're gonna apply this to the convergence of martingales again. So how do we prove this? So first, let's take the stopping time, t, which is going to be the infimum of m, such that xm is larger or equal to lambda. Sorry, yeah. So this is a stopping time, but we're also going to take the infimum with n. This is still a stopping time and is bounded by n. Okay, so let's see on A, on the event that we want to bound. Let's take a look at the definition of A again. On A, the maximum of our submartingale is larger than lambda. So in particular, at some point we have been above lambda. So that means that our process at time t has been larger or equal to lambda. Let us make a picture. So if we have here our process, here is lambda, and our process at some point goes above it, that's what happens because the maximum is larger than lambda. It's clear that this time, which is the first time we go above lambda, is going to be attained, and x at that time is going to be larger or equal to lambda. Okay, so this means that we can bound the expectation of xn on the event, xt, on the event A by lambda times the expectation of the indicator function. Why? Because on this event we can replace xt by lambda, and it's still an inequality in this direction. And this is just lambda times the probability of A. So we have half of our inequality here. We almost have lambda p smaller or equal than this expectation, except that we have a t here and not an n, which is what we wanted. So t is smaller or equal to n, but we don't have an n here. And what we'd really like to say, so this is a bad proof, is that lambda times the probability of A, first it's smaller or equal than the expectation of xt indicator of A, and since this is a submartingale, by the previous theorem we saw about optional stopping, we can replace this by xn, and we are done. But this is bad because the optional stopping theorem doesn't have this indicator function here, so we cannot use it. What we have is just this inequality. We can't use the optional stopping here. So let's use the optional stopping the correct way, right? So we know that the expectation of xn is larger or equal than the expectation of xt. This is something we know because t is a stopping time smaller or equal to n. Now, another observation is that outside of n, what's happening, so what's the event A again? A is that the maximum is above lambda. So if the maximum is not above lambda, it means that our process stayed its whole time here, below lambda. So on A complement, the time t, the first time that we cross above lambda, oops, sorry, here should be strictly bigger. So our first time that we cross lambda didn't happen. So t on A complement is equal to n. So here, t is equal to n. So now we have everything to finish the proof. We know that expectation of xn can be split, of xt, can be split into the expectation of xt times the indicator function of A plus the expectation of xt times the indicator function of A complement. But on A complement, t is n. So we can rewrite this as the expectation of xt indicator of A plus the expectation of xn indicator of A complement. And the same can be done with n. Expectation of xn is xn indicator of A plus xn indicator of A complement. So we know that this thing here is larger or equal to the above. So we know that the expectation of xn indicator of A is the expectation of xn indicator of A complement is larger or equal than what's above, xt xn. Now the second terms are just the same, and we got the inequality that we wanted. Not only xn is larger than xt in expectation, but also if we introduce these indicator functions. So now this bad proof is not a bad proof anymore. The above inequality has been proved to be correct. So we get that lambda times the probability of A is smaller or equal than the expectation of xn indicator of A as desired. This part we have proved earlier. So this is the proof of Doobs inequality. And again, it's an interesting relationship between the maximum and the variable at the end of the process. And it has been proved using optional stopping here. Although it's an optional stopping, it's a very simple optional stopping result that has bounded stopping times. So that's it. In the next class, we're gonna use this Doobs inequality to talk about moments of martingales. We're gonna bound the moment of maxima of martingales.